So we can do something that is much faster than what we did before. Namely, instead of asking Maple to compute this number here and then round it off exactly, we can ask Maple to evaluate it and then round it off. Right? And presumably Maple already does this. So I mean, when you try to compute these numbers, when you have to round it down, of course, it doesn't really matter how many decimals you have. You just need to be able to compute the integer part of the number well enough so that you can round it down correctly. Right? But what I'm going to do is I'm simply going to ask Maple to do an evaluation. That is going to be faster, but of course it's not going to work. The reason why it's not going to work, I mean, this is the correct number, and this is what I get out of Fibonacci 4, is that I'm using fixed precision in Maple, usually 10 digits. So the number that is going to be computed here, if it's computed with 10 digits precision, then when we round it off, we will see that we have a lot of zeros here, right? Because essentially Maple knows this as 3.5 times 2 to the times 10 to the appropriate power of 10. And so you can see that I get something which is pretty close to correct in the beginning, but as we reach the end of the number, this is wrong. But of course, this was also me doing something fairly stupid. I had just asked it to take the number and round it off to 10 digits, and that's not going to work. I could try to say, well, let's round it off to the correct number of digits. So I'm asking Maple to work with the correct um, precision. And what then happens is that we sort of know how fast these numbers grow. Right? They grow like this number to the n. So we have a very good idea of how big these numbers are. And if I want to know how many digits they have, I just have to take this number and compute its base 10 logarithm, and then that number will give me the number of digits that I get for each n. And that number turns out to be 0.20 something. So I will round it up to 0.21. And then actually, this is hard proof. I could prove this, that the number of digits is given by this expression here. N is the number that I'm putting into the Fibonacci numbers, times 0.21. And then I add another one for, because I need an extra digits to make room for, it's like, 100 is 10 to the second, but I need 3 digits to write it up. So that's why I add 1. Now I will have the correct size, so that's my Fibonacci 5. But you can see it's still not correct. Right? This is now much closer. I have 0.75 and 0.62. And of course, what's going on here is that since I'm using fixed precision, so in this case, n is 100, so the number of digits that I'm asking Maple to work with is 22. So when I work with 22 digits of precision, I will get some round-off errors. And that's not so surprising because the 22 digits are essentially spoken for in the number that I have up in the beginning. So there's very little room to have the computation in the decimals so that I'm sure that things are rounded off correctly. Now, in order to deal with these kind of issues, Maple has something built in called interval arithmetic that may be useful for you in your second assignment. It works the way that if I compute a number, for instance, the number that we just looked at, I can say, now make a computation with 22 digits of precision and see what you get. And so what Maple will do is it will say, suppose I have a number given by a floating point description like 3.14. Right? So 3.14, what does that mean? Well, actually, it means all the numbers that you would round off to 3.14. So those are the numbers between 3.135 and 3.145. Right? Those are the numbers that would be rounded off to 3.14. And so now when you think of a data given by a little interval, then you can also say when I'm doing computations, of course, my precision will usually deteriorate because I have, as I do these computations, my errors will accumulate. And so Maple keeps track of this. And so it will simply tell you that if you work with 22 digits of precision, the number that you get out is with certainty in this interval. Right? So it's not saying precisely what this number is rounded off to. It says that it's in this interval. And then you can see the problem with this computation that I did is that the precision is not big enough to round off correctly. I can do this maybe better by computing this number here, right? So I've now subtracted the true Fibonacci value using Fibonacci 3, and I get a number, says Maple, that's between roughly minus 50 and plus 50. But that's too much in order to enable me to round off correctly. But I can fix this by having more digits, right? So I can use 23 digits. Now I'm between minus 4.3 and plus 5 plus 3. So that's still not good enough. I can go 24, and now it's okay, right? Why is it okay? Well, the error that I have is somewhere between 1 and 0. So it's between 0.01 and 0.98. That's pretty close to 0 and 1 respectively, but since I know that the error is in this interval and I'm intending to round off the number anyway, this is going to be fine. Right? If I had a negative number, then of course, when I round down, I may get something that is it's too big. If I had a number that's bigger than too small. If I had a number that was bigger than 1, then when I round off, I may get something which is too big. So I can use this to be a little bit more systematic. I've written a little program called How Many Extra Digits, and the way it works is that it simply says, well, can I get I start with the formula that I had before, n times 0.21 plus 1, and then I say, okay, does that work? What does it mean to work? It means that when I do the shake computation, I get something which falls in the unit interval. If not, then I will increase the number of digits and I'll try again. And I'll increase the number of digits and try again. And just like in the example I had, I will have to increase it by 2 in order to get the correct computation. And then I could do this systematically, say for 100, 200, and 300, and so on. Sometimes I need 2, sometimes I need 3 digits. But as you can see, as I go towards bigger numbers, actually I don't need extra digits. And I'm pretty sure that's because the number 0.21 is slightly bigger than the base 10 logarithm of the golden mean, so that's 1 plus square root of 5 divided by 2. So this number here, I need to eval it. This number here is exactly something wrong. Yes, try again. This number here is exactly the number of digits that I get for that I need for n, and you see this is slightly smaller than 0.21. Right? So as n increases, then I get extra digits automatically just by this being bigger than 0.21. Okay, so what I'm going to do, so what this means is that it looks like if I say put in extra 6 digits or something like, just to be on the safe side, then I should be okay always. I certainly get the right number here, and now I can use my f-timing command on Fibonacci 7, see what I get. That was not so good. Probably forgot how I spelled it. F-timing, oh yeah. Forgot to tell it 10 seconds. And what you'll see here is that this is faster. We get all the way to 2 to the 23, which is a record compared to 2 to the 22 that I had before. But of course, this is a little bit shaky in the sense that I'm not 100% sure that this works, right? This is just based on the observation that if I add 3 digits, and then I went up to 6 by sort of saying, well, that's bigger than 3. So I don't think I can be absolutely certain that this works, but if you check these numbers, they are actually correct. So that is maybe a strange mixture of using floating point numbers and exact computations, but this is often a way of getting faster numbers.